So let's continue the limit problems. Here we have a limit x approaches 2 of this rational polynomial, and if you do direct substitution into this polynomial, you see that you end up with 0 over 0. And 0 over 0, since it's undefined, you didn't get anywhere with the limit. So what we need to do in this case is use a little bit of algebra. So with a little bit of algebra, what you can do is factor the numerator and denominator, and when you do that, you see x minus 2 is a common factor. So once that's removed, because in the limit x is not equal to 2, x is simply close to 2. So once that's removed, you end up with the limit of this rational function, and then you can use direct substitution and get 3 over 2. Now in this limit, we want to look at the limit as x approaches 3 from above. So if we did direct substitution here, we would have 1 over 0, which is undefined. So we need to do something else. And so if you look at a table of values where we look at a sequence of values for x that's approaching 3 but strictly larger than 3, then the image of those points under this function, you can see that in this column here. And so this gets really, you can see it's getting larger and larger. So this is on the order of 10, 10 squared, 10 cubed, 10 to the 4. This is like 17,000. So as x gets close to 3 but is strictly larger than 3, we can see that that function becomes unbounded. Now you could do this in your calculator also. You have to define the function and then go to table setup and make sure independent variable is set to ask. And if you do that, you can have a very similar result in your you can see that in your calculator from a table. So what you can conclude from this, as in the limit, this difference in the denominator is becoming very, very small, and so that ratio goes to infinity. Here we want to know, we want to decide what are the vertical asymptotes for this function. Now this isn't actually a calculus question, but we'll look at it anyway because I think we did look at this in class. So the default graph for this is kind of weird looking. It looks like this, but this graph only looks like this because when the graph is made, the pixels in your screen are either turned on or turned off. It doesn't draw the vertical asymptotes correctly. So these blips here, this one and this one, that indicates there is some kind of vertical asymptotic behavior, but we need to do a little bit of analysis to see where those points are. So if we looked at this function and we see in the denominator it's a difference of squares, so that's factorable. So we see then that the if we look at the zeros of the denominator, those zeros will occur at positive and negative 7. And that's where these blips are in the graph. So if we had a slightly better graph, this isn't that much better, but it's a little bit better. You can see at x equal to 7, from below it's going to negative infinity, from above it's going to positive infinity. At x, that's at x equal to 7. At x equal to negative 7, we have similar behavior, but you can see the graphing utility that I used here, it was connecting points. So it turned this pixel on, but then it connected the points and then turned this pixel on. So this like vertical line here is really an artifact of the drawing program. It is not an actual part of the graph. So to draw an accurate graph for this, you would need a dotted vertical line at positive and negative 7 to indicate the vertical asymptotes. As x approaches negative 7 from below, this goes to positive infinity. As x approaches negative 7 from above, it goes to negative infinity. The vertical asymptotes, again, are at positive and negative 7. Similar question, we want to know what the vertical asymptotes are. So the default graph, you can see there's some blips here. I turned the axis off so that this is just a graph of the ordered pairs that are plotted by this function. And you can see something's happening here and something's happening here. And on the left case, this vertical line, again, is an artifact of the drawing program. It's not an actual part of the graph. And it does indicate that there's a vertical asymptote there. But the drawing program connected the dots, connected the pixels, and that's why you have this vertical line here. That's not an actual part of the graph. So in terms of the algebra, if you factor the denominator, you can see that there is a common factor, and that common factor will be 1 for all values of x not equal to 3. But at x equal to 3, this function is not defined. And so we can, for all values of x not equal to 3, the function's equal to this last expression here. And so from there you can see that there's going to be a vertical asymptote when x is equal to 0 and also when x is equal to -3. When you look at a default graph, that will make sense. Here's the vertical asymptote at x equal to -3. As x approaches -3 from below, this goes off to -infinity. As x approaches -3 from above, this goes to +infinity. And similar behavior at x equal to 0. The function's not defined at x equal to 0, but as x approaches 0 from below, this goes to +infinity. As x approaches 0 from above, it goes to -infinity. The last set of questions we want to look at now are these two limits. And in the first case, we have a limit as x goes to infinity. So in this case, this is pretty straightforward. This rational function in the denominator, as x grows large, that ratio goes to 0. So this approaches 3/6 or 1/2. Now for the second rational function, it's not quite as obvious, I suppose, because the numerator grows without bound, the denominator grows without bound. You really have infinity over infinity. But what you can do is divide by the largest power of x that appears in the denominator. So that's 1/x, or it's x. So you would multiply by 1/x over itself. That's equivalent to dividing both the numerator and denominator by x. And so what happens in that case is, here's the algebra. You get this expression. And so x over x is a 1 for all values of x not equal to 0, but we're not interested in behavior at x equal to 0 here. So this is the result. And as x goes to infinity, this term 1/x goes to 0, and this term 7/x goes to 0. So in the limit, you end up with 6/8 or 3/4.